Star clusters. Some of the Milky Way stars are gravitationally bound together in groups called star clusters. There are two types of star clusters, open clusters and globular clusters. Open clusters contain up to a few hundred members in a volume typically 7 to 20 light years across. The Pleiades, or the Seven Sisters it's also called, is an excellent example of an open cluster. They're also called galactic clusters since most lie in the galactic disk. They're formed when interstellar gas clouds are compressed and collapse upon entering the Milky Way's spiral arms. About 20,000 open clusters currently exist, many of them obscured by dust in the galactic disk. Within spiral arms, very young stars may group together in a loose association a few hundred light years across. Single large open clusters near their center, and the birthing gas and dust is still present. After hundreds of millions of years, the stars gradually leave and the cluster dissipates. Here are some pictures of different open clusters. The Pleiades, we said, is one example. There's some other ones. M67. M just refers to a certain catalog, the Messier catalog, object number 67. Or NGC is the new general catalog, object number 3293. They're just books that contain locations of different objects and describe them. These are all open clusters. Globular clusters contain far more stars than an open cluster, from a few 100,000 to several million per cluster. They have large radii, maybe 40 to 60 light years across, and a strong gravity pulls the stars into a ball denser than that found in open stars. About 150 to 200 globular clusters outline the halo and bulge of the Milky Way. Here are two pictures of globular clusters. This is M13. So 40 to 60 light years across, but it might have 1 million stars in it. They're really brilliant objects and a lot of fun to see in a telescope. So open and globular clusters reflect the properties of population 1 and population 2 stars. Open clusters are generally population 1, globular clusters are population 2. So in order to understand clusters, we must first discuss the types of stars around us in ways other than temperature and luminosity. So we can take a stellar census. It counts that list all the known stars of a given type in a region of space is called a stellar census. All star types are represented in our galaxy. By analyzing the relative number of stars of each type, we can deduce the galaxy's history. Brings us to something called the mass function. From a stellar census, one can derive the number of stars of each mass, typically known as the mass function. Mass, as you know, determines the life cycle of a star. The evolution of our galaxy will then depend on how many stars of each type it contains. A galaxy with only massive stars will evolve quickly, and how fast each type is created. Fast creation will deplete gas resources quickly. So we get some results from our galaxy. Dividing the number of stars in our galaxy by its age gives a star creation rate of about 3 to 5 stars per year. The most numerous stars tend to be dim, cool red dwarfs, about a half solar mass. The average mass for stars in our galaxy is about 1 solar mass. Stars more massive than 100 solar masses are rare. Current research suggests that brown dwarfs, or failed stars, of mass less than 0.08 solar masses, are more numerous than ordinary stars. It's important to be aware of selection effects when interpreting data. Absence of evidence is not evidence of absence. In other words, there may be things out there we just cannot see. So the two stellar populations, population 1 stars, are generally young, 1 million to 1 billion years old. Their color is blue generally, and they are located in the disk and really concentrated in the spiral arms of the galaxy. Their orbit is approximately circular in the disk of the galaxy, and they have a high heavy element content similar to that of the Sun. Population 2 stars are old, about 10 to the 10th years, or 10 billion years. The color is red, and their location is out in the halo of the galaxy. I think of the galaxy as a basketball with most everything in a line that goes right through the center, so the spiral but there's some stuff in this spherical region. That's called the halo. The bulge is the center bulge here. That's the location of population 2 stars. And their orbits can go way out and plunge through the disk. And they have very low heavy element content, 100 to 1,000 times less heavy elements than in the Sun. Now, division of stars into just 2 groups can be an oversimplification. Actually, the Sun doesn't really fit into either category, but it's typically thought of as a population 1 star. So that inspires creating subgroups. Subdivide each population into extreme and intermediate, or oldest population, sometimes used for stars like the Sun. Now, the 2 populations show that star formation has not occurred continuously. Population 2 stars formed in a major burst at the galaxy's birth during the initial collapse of our universe. Population 1 stars formed much later and are still forming today. Population 1 stars are used to map the spiral arms and vicinity around the Sun. Now, astronomers assume that when you see a cluster of stars, they were all formed at about the same time. There are several reasons for believing this. High-mass stars, the OB stars, which have to be young since they evolve so fast, are usually found in groups and clusters. And stars ought to form in groups since large interstellar clouds are more unstable than small ones. It's theoretically very unlikely for hundreds of stars to come together to form a new cluster unless they were born that way. And the HR diagrams of clusters indicate that they all have a definite age. The stars in a cluster have a wide variety of masses. If they were born at the same time, they must be at different evolutionary stages. And we can see this by plotting an HR diagram for all the stars in one particular cluster. So, for example, this is the HR diagram of the stars in cluster NGC 2264. Note that most of the stars are above the main sequence, as predicted by a young cluster. All these stars have yet to get to the main sequence. The higher mass ones are already on the main sequence, and the even higher mass ones may have already burned up all of its hydrogen and are starting off into the giant phase. This is a picture of that same cluster. Now remember, different stars, depending on their mass, take different amount of time to reach the main sequence. Small mass ones may take up to 10 million years, or large mass ones only 160,000 years. So after a cluster is born, more or less at the same time, the high mass stars go through their main sequence lives more quickly than the low mass stars. So the overall appearance of the HR diagram for the cluster changes. At 1 million years, stars in this part of the HR diagram are still protostars. They haven't reached the main sequence. Whereas the supermassive ones have already become a star, lived out their lives, and are in their death throes. And so by looking then at the turning off point of where stars are dying, I could tell the age of a star cluster. So the astronomers can use the HR diagrams to estimate the time since the cluster was formed. This is one of the very few ways there is to estimating the ages of stars. In 67, the globular cluster we were looking at early, the turnoff point is relatively far down, so this means it's a very old cluster. Or the Pleiades, it's kind of a medium age, or the one we're looking at is a very young cluster. Now, the reason for the difference between the 2 types of cluster is that globular clusters were formed when the galaxy was young, and not many metals had been made inside stars yet. The open clusters were made more recently, when the interstellar material was richer in metals. The final difference between the 2 types of the cluster is their location in the galaxy, and we'll return to this later. Now, except for globular clusters, which can hold themselves together indefinitely, clusters eventually break up and drift apart. And one reason for this is the differential rotation of the galaxy, which we'll talk about later. Our Sun was probably a member of a cluster when it was young, but we cannot identify any of its siblings now.